In this lesson, we will explain the fundamental processes behind the operation of lithium-ion batteries, highlighting the reasons why this energy storage technology has become the most successful. Energy accessibility, increased utilization of intermittent renewable resources, cleaner cities, and the rise of electrical vehicles share a common factor. Significant progress in these areas has been driven by over than 40 years of research advancements in high-specific energy batteries, particularly lithium-ion batteries. The combination of high cell voltage and excellent specific capacity makes lithium-ion batteries the most energy-dense rechargeable batteries available today. They can achieve specific capacities 200 to 300 watt-hour per kilogram, significantly outperforming lead-acid batteries, which typically offer only 30 to 40 watt-hour per kilogram. However, this impressive energy performance is not solely due to the inherent chemistry and electrochemical process of lithium-ion batteries, but also stems from their unique cell design and architecture. Since the early 80s, intensive efforts have been dedicated to developing rechargeable batteries using lithium-ion intercalation compounds. These advancements have revolutionized portable electronics and now serve as a crucial enabling technology for energy transition and sustainable mobility. Like all batteries, lithium-ion batteries are composed of cells containing a negative electrode, a positive electrode, an electrolyte, and a separator. The electrolyte facilitates ion conduction within the cell, enabling current flow, while the separator prevents direct contact between the electrodes, preventing short circuits. The negative electrode, known as the anode, undergoes spontaneous oxidation during discharge, releasing electrons. Conversely, the positive electrode, or cathode, experiences spontaneous reduction, drawing in electrons. While electrons travel through the external circuit, the internal current within the cell is driven by the movement of lithium ions. These ions, which originate from the dissolved salt in the electrolyte, act as charge carriers, maintaining the balance of electrical charges as energy is stored and released within the electrodes. Both the negative and positive electrodes utilize lithium-ion intercalation compounds, allowing them to host lithium ions during redox reaction with minimal structural changes. The host material should be as lightweight as possible, while accommodating a large number of lithium ions to achieve a high specific capacity. Additionally, these mixed conductors must possess sufficient electronic and ionic conductivity to enable batteries with a strong current response. Modern lithium-ion batteries feature a graphite anode, while the cathode is typically composed of transition metal oxides, such as cobalt, manganese, or nickel, or lithium phosphate. During discharge, electrons travel from the lithiated graphite anode to the positive electrode via an external circuit, while lithium ions simultaneously migrate through the separator from the anode to the cathode. During charging, the process reverses. Electrons flow from the positive to the negative electrode through the external circuit, while lithium ions move from the lithiated metal oxide cathode back to the graphite anode. The primary change occurring in this process is the shifting of lithium ions between electrodes. As they shuttle back and forth during charge and discharge cycles, much like as a rocking chair, lithium-ion batteries are often referred to as rocking chair batteries. The composition of the electrolyte plays a crucial role in lithium-ion batteries, as their electrodes are highly reactive to oxidation and reduction. Lithiated graphite, with its relative low potential, around 100 or 200 mV versus lithium plus lithium, acts as a powerful reducing agent. Conversely, some delithiated cathodes operating above 3.5 volt versus lithium plus lithium exhibit strong oxidative properties. The electrolyte used commercially in lithium-ion batteries is a solution containing a lithium salt with a fluorinate anion, typically the hexafluorophosphate or the trifluorosulfonimide, and a mixture of organic carbonates as solvents. The fluoride salt is used to control the chemistry at the anode interface, while the carbonate mixture consists of a cyclic system, like ethylene carbonate, with high dielectric properties but high viscosity, and the linear system, dimethyl carbonate or ethyl carbonate, to reduce the viscosity of the solution. Different shapes and chemistry of lithium-ion batteries are available. The shapes can be divided into cylindrical and prismatic, whereas the prismatic shape can be further divided in regard to the housing stability in hard case or pouch. The manufacturing process of lithium-ion batteries comprises the electrode, the cell, and the battery system manufacturing. Electrode manufacturing provides the anode and the cathode films needed for the subsequent cell manufacturing. It is an automatic processing of layers of active materials casted on current collectors, metal foils of copper for the anode and aluminum for the cathode, that are then laminated with separator membranes. Cell manufacturing consists in stacking and shaping the different layers to fit different sites. It includes component assembly in the cells and electrochemical activation, formation cycles. Battery system manufacturing relates to the electrical connection of the battery cells and their implementation with the battery management system. Overall, these steps greatly impact the cost, energy consumption, and might contribute with about 25% to the cost of marketed cells. These high energy consumption steps can result in a huge amount of greenhouse gas emissions and require further progresses that make less environmentally friendly manufacturing. In addition, today lithium-ion batteries utilize various cathode materials, including lithium cobalt oxide, lithium nickel manganese cobalt oxide, lithium iron phosphate, and lithium nickel cobalt aluminum oxide. These batteries depend on critical metals such as lithium, cobalt, nickel, and manganese, which require mining and refining processes that have significant environmental and socio-economical impacts. For instance, cobalt is mainly extracted in the Democratic Republic of Congo, while mining practices have raised concerns regarding labor conditions and environmental harm. Likewise, lithium extraction, especially from brine sources in South America, demands large amounts of water, impacting local ecosystems and communities. As the global demand for lithium-ion batteries surges, particularly with the rise of electric vehicles and renewable energy storage, it is crucial to increase attention to sustainable and ethical sourcing of these metals. It is now evident that advancing battery technology demands a comprehensive and innovative approach that fully aligns with the European Strategic Energy Technology Set Plan Action No. 7, the Battery Europe Strategic Research Agenda for Batteries 2020, and the Battery 2030 Plus Roadmap. The SET plan outlines strategies aimed at enhancing energy performance, promoting sustainable manufacturing practices, utilizing green raw materials, and facilitating the recycling of lithium-ion batteries. Through the Strategic Action Plan on batteries, the European Commission is fostering a competitive, sustainable, and innovative battery ecosystem across Europe.